Thank you very much, Chris, and good evening. It always gives me tremendous pleasure to walk the 20 meters from behind that wall down here and share with you some of the latest things that have been going on in the London Institute of Mathematical Sciences. Now, let me find my clicker first. Let's see if this works. Faraday induction. Now, it feels like these days, I meet somebody in a pub or at a party, right? I strike up a conversation, I tell them I'm a mathematician. Invariably, the conversation drifts to, what do you think about AI? Right? You tell them I'm a scientist, they think about AI. Now, back in the day when I tell people I'm a mathematical physicist, they ask, what is the latest of string theory? What is quantum gravity? And if you tell them, of course, what I work on is, if you tell them you work on algebraic geometry, that ends the conversation right there again. You're never spoken to again. But these days, it's all about AI. Now, interestingly enough, there are only two types of people I meet. Okay? On the one extreme, you got people saying, dude, the singularity is coming, and the AI is going to take over our jobs and kill us all, right? And on the other extreme, you got people saying, whatevs. This is just like total hype, right? Bit of compute, maybe a little more powerful machines now, whatever. So the lecture tonight, I hope to inform you a little bit about AI for mathematics and let you be the judge of where on this balance you would sit. Of course, as it is with all things in life, it's neither extreme. But where exactly you would like to sit is, I'll let you be the judge. Now, I'm by no means an expert in AI, but I've been fortunate and very privileged to be one of the people who brought AI into mathematics and theoretical physics about 8 years ago. And since then, it's been a growing and vibrant community. AI for math is very much a thing now. Now we're a community about hundreds, on the order of hundreds of mathematicians. And we all believe that, in some sense, AI is poised right now, as we speak, to change the very nature of how mathematics is done. Indeed, there was a Nature piece by our director, Thomas Fink, last year called AI is poised to change how mathematics is done, to aid mathematics in its very foundation, right? So precisely because mathematical data is exactly the kind of thing that AI is good at. And I'm going to define for you what mathematical data is. So since I'm a mathematician, I need definitions. What is artificial intelligence? What is AI? Now, this turned out to be a tremendously difficult question. And I cannot even give you an answer precisely. We had the great Professor Geoffrey Hinton, who was here just a few months ago, he got the Nobel Prize for this, so just listen to how he defines it. I will give you a little bit of take of what AI is for a mathematician in the best way I can. That I can. Well, I can tell you where the word first appeared. John McCarthy was a professor of computer science in Dartmouth College in America. In 1955, he and a bunch of people got together. I know this is what drives. By the way, this is what drives academics. It's all about grant proposals. Okay, so these guys were writing a grant proposal. That's the title. It's called a proposal, right? So they wanted to come up with all the stuff that, 1950s is just when beginnings of the big scale computing, right? They were trying to think about how to imitate the human mind, right? And they were thinking like, we need something much, much cooler and sexier than compute, right? So the word McCarthy and friends came up with was artificial intelligence. In fact, McCarthy wanted it to be computational intelligence, but that wasn't cool enough. So he just invented this word, artificial intelligence, and the word got stuck. And that's the first time in print that the word artificial intelligence in 1955. Interesting, right? So here is at least my best attempt to explain to a mathematician like myself what is AI. Now, okay, I promise there won't be too many questions, but you got to have a couple just for fun. So the basic mantra goes under as follows, right? Connectivism leads to emergence. And I'm absolutely sure that meant absolutely nothing to you. Okay, now let me explain what that means. Traditionally, what do we do as mathematicians, right? We got functions and mappings that take certain input, and we try to give some kind of output. If you think about what that is, modeling the world, whether it's the real world around us, or universes that mathematicians make up in their minds, in some sense, it's about how to take inputs to outputs, where here's a function that takes this value to this, and so on and so forth. Now, you can imagine playing around with simple functions, and I won't even bore you with the details of such functions, is not going to get you very far. If you want to predict the weather, it's very unlikely there's going to be a single function, no matter how complicated. It's not going to be a bunch of sines, right? It's not going to be a bunch of, or even more complicated functions like Bessel functions. So around about 1950s, people were thinking, well, what if I don't just have a single function, but a whole network of them hooked up together? Each one of these bubbles is one of these functions. And connect them. So the buzzword became connectivism. Apparently, this buzzword completely fell out of fashion by the 1980s because it was just too long. And now what we have here is what's traditionally called a neural network. I think Professor Hinton defined this very well. So a neural network, all it is, it sounds mysterious, is mathematicians and computer scientists and physicists and engineers trying to imitate the human brain in linking together activation functions to get something much more complicated. Now, I think this is a very good definition of what AI is, in the sense that any kind of artificial intelligence, where at some level, whether it's language models that I'm going to talk about later, at some level it's going to involve this kind of connectivity of some form of neural network. Like, in fact, a large language model is a particular type of neural network. So that's where this comes about. So I hope you have at least a working definition. This is not precise for a mathematician by any standards. A working definition of what artificial intelligence is. It's something that involves this kind of structure. The fact that this kind of structure can indeed imitate to arbitrary precision any kind of input and any kind of output is a theorem. So I promised the next slide is pure. Get ready. You ready? The next slide is purely to scare you. They're called universal approximation theorems. Now, if I read these out, it'll take the rest of the lecture, so I won't read them out. But this is just to show that there's an entire field of mathematics for artificial intelligence that works on proving theorems that structures of such a type can indeed imitate anything. So that's the take-home message. As long as it's complicated enough. Mathematicians in the audience, you can admire all of this L2 convergence and whatnot. Have a field day with that. So here are some of the key moments in AI, right? If you think about this imitation of the human neural network to try to model anything, okay? This is not, by the way, this is not all of the key moments, obviously, but here's someone that are particularly striking. So I think in some sense, it dates at least as far back as Descartes, okay? Descartes in 1617 had the idea of the bête machine, the beast machine, in which I think he coined the word automaton. The idea that we could imitate humans by creating a machine that imitates us. I mean, it's 1617, right? It's pretty impressive. Well, this is Descartes. It's a cool guy. And then in 1842, Ada Lovelace, one of the early pioneers of this entire field of computing, right? In fact, I believe she hung out here in the RI because she was the daughter of Byron, and Byron was friends with Humphrey Davy. So she was, of course, famous for working with Charles Babbage in inventing the analytical engine. She was the first programmer to the analytical engine. I have no idea what the analytical engine is, but just think some kind of a steam-powered crank calculator that's got lots of buttons. See, that's my knowledge of the analytical engine. But she said something quite prescient, which is this fantastic quote. She said, the analytical engine might one day compose elaborate and scientific pieces of music of any degree of complexity. Right? That's a beautiful and prescient saying from 1842. In some sense, she's kind of predicted what ChatGPT can do in terms of writing music for you. Right? Moving on, 1949, the great mathematician and computer scientist Alan Turing came up with a test. He didn't call it the Turing test. We call it the Turing test after him. And what this test basically is, you got a black screen, you're typing, and behind that screen is either a person or a machine. Can this person, who is the real human, tell the difference whether you're interacting with a machine or a human? If you can't tell the difference anymore, you pass the Turing test. This is one of the most amazing tests of modern computing that you could ever think of, right? At the point, in 1949, this was like, oh my goodness, this is way beyond what we're capable of doing. Okay, just bear that in mind. Turing test, 1949. Okay, moving on. 1956, the Dartmouth Conference, where the word artificial intelligence first came about because they needed money for grants. Money for grants, big idea. Anybody wants to give money to my research, please. Shortly thereafter, the perceptron was invented. Now, you can tell that this is a word that came from the 1950s because it ended in tron, like everything else in the 1950s. What the perceptron was an amazing thing that tried to realize the theoretical possibility of the 1956 conference. What these guys did in the basement of, I think, Penn, MIT, they had a whole wall, like this big, of cadmium sulfide photoreceptors. I have no idea what that is. Go ask a chemist. And they shone flashlights onto this connected network of cadmium sulfide photoreceptors to try to imitate computation. And they called that thing the perceptron. That's quite amazing. That, in some sense, is the beginning of the artificial neural network. Okay, then the field kind of got stuck up a little bit because people were busy fighting Cold Wars and landing people on the moon. And then until the 1980s, where these gentlemen came up with a theoretical basis of concrete ideas of the modern artificial network. And of course, they both got the Nobel Prize, so that's why they're very happy. And we, indeed, we're very, very honored to have had Professor Hinton here, right here, giving you, those who were here, this lecture. I mean, it was a beautiful lecture he gave here about what AI is. Okay, moving on. In 97, IBM's Deep Blue beat humans in chess. So I was young back then, and at that point, I stopped being interested in chess. So this is completely astereotypical of mathematicians. I have zero interest in chess precisely because it's solved. And kind of like for a mathematician, it's solved, why it's not interesting anymore. And moving on a little bit further, Go was a much, much more complicated game than chess. And that was thought to be impossible to be solved by any kind of AI. DeepMind broke that and surprised everyone. In 2012, it solved Go. In fact, we have several DeepMind friends here. I think my friend Bhavik is there, who worked with DeepMind. Torger Payos, who was the head of AlphaGo, is here, I think, somewhere. And so you can see, spanning 4 centuries, especially the beginning part of the 20th century and the 21st century, was really, now we're here. We have no idea how fast this is growing. Right? So this is where we are, somewhere over here. So I can't tell you where we are, ask Professor Hinton, but here in mathematics, I hope you'll get an idea where we are. Okay, second definition. At some point, I'm going to start saying definition, theorem, proof, and we'll be here all day. What is mathematics? Right? This talk is about AI for mathematics. This actually is a much easier question to answer. I have a much better answer for you. What actually is mathematics? I think the best definition of what mathematics is the quote of the great G.H. Hardy. Right? Oh, by the way, if you've not seen The Man Who Knew Infinity, about the friendship and collaboration between Hardy and Ramanujan, please watch it. It's one of the most, I was flood of tears watching that movie. It's one of the best science movies ever made. Geoffrey Hardy was one of the greatest number theorists of the 20th century. He gave this definition. That a mathematician is a painter or a poet and is a maker of patterns. And I think that's the most wonderful definition of mathematics. Mathematics is a natural language fit to study patterns. That's all we do. Sums, sequences, pictures, geometry. So that's it. So I've defined for you what AI is, something that involves networks, and I've defined for you what mathematics is in the words of Hardy. Now, as I get older, I get a little more philosophical. Just because I define for what is mathematics, how do we actually do mathematics? Like, I mean, as a practitioner, what do we actually do from day to day, right? And so I was invited by Nature last year to write a review precisely about this whole field of AI-driven mathematics and pure mathematics and theoretical physics. And it got me thinking about how we actually do mathematics. So this talk now, it's going to be about these three directions, and I'm going to define them one by one: bottom-up, top-down, and metamathematics, and how AI is poised to fundamentally change how each of these three directions in which we actually do mathematics. Okay, so that's, get ready for a trilogy of things. Now, you may ask me, how did I get into this whole field, right? I mean, I've given two talks here. One was about geometry, and one's about mathematical physics. That's my bread and butter. Right? And how did I even get into AI? What forced me to learn AI from Coursera and taking courses online? Well, the answer is actually very, very simple. In 2017, my son was born. And that meant I had a beautiful little girl and an infant son. That means arrivederci, sleep. All right? I had a paternity leave at the time. You don't sleep anymore. In fact, at 3 a.m., you're like wide awake. You know, what do I do with my life? Well, what do I do with my life? Well, I'm going to learn machine learning. And as one does, right? And what's interesting, right? I think, so I work in this field called mathematical physics that's between string theory and algebraic geometry. So what I had in particular were databases of shapes called Calabi-Yau manifolds, databases that's tens of thousands, hundreds of thousands. I had it on my laptop. I wasn't sleeping at 3 a.m. I was like, why don't I pass these geometries known as Calabi-Yau manifolds and try to compute topological invariance? By the way, these words are supposed to not mean anything for you, but it's a very, very difficult computation in mathematics I've been doing my entire career. Now, I had a bunch of these input-output, and I fed them into a neural network. And I was like, yeah, this is not going to work. This is 3 a.m., I'm tired. And the neural network is very quickly fitting itself in a mysterious way and predicting this topological invariance without any knowledge of mathematics. It was doing something that I clearly had no idea what was going on. And then, I tried to share with the community what was happening. So thanks to my daughter and my son. So I wrote this paper at the time, 2017, called Machine Learning, the String Landscape, which is one of the very first papers for AI for mathematics. Now, interestingly, so that's how I got into this whole field, right? Interestingly, at the time, I was commissioned by Springer Nature to write a textbook on my subject of Calabi-Yaus for mathematical physics and algebraic geometry. So the title originally was meant to be The Calabi-Yau Landscape from Geometry to Physics. But because I was trying to, first of all, teach myself how to, what is artificial intelligence, what is machine learning, I added this. The best way to learn a subject is to write a textbook in it. And this very appropriately, very timely became the first textbook on the subject of AI for math. There's plenty of stuff for math for AI, and there's plenty of stuff on AI for, experimental physics. That's been for years, right? But for pure math, it was a bit crazy thing to do. So I read this book. Please buy this book so I can get my £50 royalties per year. So I don't. Academic publishing is really crap. But anyhow, at least I get my £50, so I don't have to sell my left kidney. While you're at it, please buy also this book, which came out a year later, which is actually the first editorial on the subject. It's called Machine Learning in Pure Mathematics and Theoretical Physics. And this one is done with World Scientific, and I'm very happy to have my colleague Long here to do this. So please buy this one, so I get the other 50 pounds, so I can now get 100 pounds, and I don't have to sell both kidneys. So that's how I got into this whole business. Let's go back. I said we're going to do 3 ways where mathematics is actually done, right? Not what mathematics is, the study of patterns, but how do we do mathematics from a day-to-day point of view? Well, let me start with bottom-up. Well, for those who know me, I cannot possibly give a talk anywhere without showing Euclid. He's the granddaddy to us all. So Euclid, in his 13 volumes of the Elements, around about 300 BC, amazing stuff, right? Started essentially what we now call mathematics. The way he wrote the Elements, it's beautiful. This is a much later Latin translation, probably from the 16th century. He gave us the idea that mathematics can be built bottom up. So you have axioms. You define your first axiom. What is a point? It's your second axiom between any 2 points on this plane. In a plane, you can there's on, etc. And then you can build up hundreds and thousands of more interesting sentences. Right? This is a beautiful example of axiomatic bottom-up mathematics, building up from foundation up. Okay. So and this goes back to Euclid. You think that well, certainly this is how mathematicians do mathematics, right? Certainly that's one. There's no dispute there. The 20th century answer to this is very, very interesting, right? That was 300 BC. In 1910, this remarkable book was published by a collaboration of Russell and Whitehead called Principia Mathematica. There's something about Brits and the title Principia Mathematica. This one has nothing to do with Newton's famous book, Principia Mathematica Philosophiae Naturalis, the mathematical principles of natural philosophy, published in London, not probably 100 meters from here. This is just the principles of mathematics. This is a very, very strange book, okay? Because this book tried to lay out the foundations, everything from Euclid up to, well, at least that was the plan. Okay, they didn't have to write a grant proposal back then because Russell was independently wealthy. So to go all the way up to 20th century, so spanning 2,000 years of mathematics, building up sentence by sentence, okay? I tried to read this book as an undergraduate, okay? Very quickly, I broke down in tears. I was like crying like a dog because, I will show you why. I think nobody's actually read this book. Because on page 362 of volume 1 of symbols that look like this, they finally proved that 1 plus 1 is equal to 2. I kid you not. You can imagine as an undergraduate while I was crying like a dog. There's a footnote, which I didn't quote here. The footnote says, this truism has been proven to be useful from time to time. So what these guys did was something very, 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 very remarkable, right? They built it from sentences that look like this, from the definition of sets, and 362 pages later, they were able to get this, right? Yeah, it's totally cool, right? But I haven't met anyone who has actually read it. I'm sure I exaggerate. Of course, logicians have read it, but this is the reason why I didn't get into logic. I went into algebraic geometry. There's a reason for this, right? In my naivete and frustration as an undergraduate, I said, this book is not for humans. And now I think back, and it's like, yeah, actually, that was a pretty wise thing I've said. This is exactly not for humans. This is the perfect book for machines, right? And before we get there, I'm advertising the next slide, which is obviously there will be machines. This has been introduced to machines. Now, you can imagine this 1910 first publication. They're going to keep on going until page 5 million, where they'll get to maybe Pythagoras' theorem, right? And then that program was killed in 20 years. This is extraordinary. In 20 years, Gödel, Church, and Turing especially Gödel's famous paper, right, on Form 1 decidable statements. What Gödel did to this whole program of axiomatizing mathematics from ground up, this bottom up, was to show a remarkable fact. And that became known as Gödel's incompleteness theorem. And that theorem basically states, within any orders of logic or any choice of language, there will always exist statements whose truth value cannot be decided. You can neither prove it's right nor wrong. So that completely kills anything of this type, right? Hold that thought, okay? Just hold these two thoughts in your mind. I'm going to refresh your mind repeatedly throughout this, right? And so Church and Turing took this further and showed explicit computational things like the Turing machine, which had Turing incomputable things. So at some level, you can think that this is perhaps, a bottom-up limitation to what AI can possibly do, right? So just park that thought for a minute. Okay, so Gödel, Church, and Turing killed this program of Principia Mathematica, but that didn't stop computer scientists. So in 1956, right after that famous conference in Dartmouth that started artificial intelligence, these guys teamed up to write this fantastic paper, which they called the logical theory machine. I have no idea. So what they did was to devise an early version of the computer. 56, right? This is before you can type. I mean, I have no idea. Punch cards? I don't know, plastic stuff. And they were able to take the axioms of Principia Mathematica in that non-human form and prove a whole set of them, like 50 to 100 of them, which is remarkable, right? So this is, in some sense, the beginning of AI, well, of computation at least, computation-assisted mathematics. And they were able to decide the truth value using machine to prove theorems, 1956. So that was 50 years ago, right? So it's kind of remarkable how fast we've grown, right? If you think about what these guys were doing, and then they kind of stopped because there were Cold Wars to fight and whatnot, but more importantly, they were limited by computation. If you want to type out the entirety, even up to volume 3 of Principia Mathematica, they didn't just have the computing power at the time, right? That's pretty obvious, right? What fundamentally changed for us right now, today? Well, it's very simple. This little thing allows any one of you to access the entirety of human knowledge at your fingertips, right? Pretty much, almost all of it. And in addition, this little thing, just this one device, is already more powerful than the entire lunar landing program of NASA in the 1960s. Right? This is what's fundamentally changed. Right? So couple that with this, what do we got today? We have MathLib. So this is a thing that the mathematics community, headed by Demora and Kevin Buzzard in Imperial, and Bavik over there, my friend, just out Imperials, I don't know which direction it is, and various other collaborations in the community to do exactly what the logical theory machine was trying to do, but for modern mathematics. In other words, input, type by hand, all of the axiomatic foundations of mathematics, line by line, and then all the proofs, line by line, until we get there. Okay, so this is called the MathLib project, and this is supposed to be lean, and it's called just MathLib lean. Just think of these two words. Within 10 years, this project of axiomatizing mathematics on the computer, it became known as the Xena project. I have no idea why it's called the Xena project. It's a cool name. Formalized the entirety of the undergraduate program in mathematics. So just to give you a flavor, these were a good chunk of my undergraduate texts that I was using in mathematics, taken in my beautiful office that you can see from behind that window. See there? At least I kept them. So it's not much, but it's not trivial either, right? So significant corpus. So everything in these books would have been typed by humans of everything. And they hit the return button in 2023, and whew, everything's consistent, right? There are no logical inconsistencies between what's been taught at the undergraduate level in Imperial. No, I didn't go to Imperial, but I went to Princeton, which I think also had a very good math program. So it's about equal amount of corpus of what was done. So this is kind of interesting, right? So this is what it looks like. Again, this is certainly not for humans, right? This is for machine, but sadly this is typed in by humans, line by line. So the full proof of Pythagoras' theorem, including all of the definitions in lean, is about 100,000 lines, which is nothing for a computer. So that's where we are. Now, our great leader, Professor Terence Tao, is a Fields medalist and widely acknowledged by all of us to be our leader. He's one of the greatest minds in human history. He wrote this beautiful paper, when was this? I think in the early 2020s, about mathematics going into this direction of machine-assisted proofs, bearing in mind Project Xena and what Lean can do for us and MathLib can do for us. Just as a bit of a caveat, there is no large-scale AI involved in this just yet. Now, we'll have about 1 million lines of code in Lean now that has most of the undergraduate level and some research level mathematics. Okay, in some small, so it's about 1 million lines, and at some point, you see where we're going to go, right? We're going to feed this into some kind of AI, and the AI will try to learn the linguistic patterns of this library, and then it might generate new ideas. And we're at the cusp of this being done. Okay, and I will mention a bit of that later. Okay, so everybody with me? Everybody's happy so far? So that was bottom up. Building up mathematics from ground up, Euclid, following the path of Euclid, and then inspired by the Principia Mathematica of Russell and Whitehead, with a hiccup by Gödel, and then into MathLib today, where we have millions of lines of MathLib today, and it is crucial. Okay, Kevin Buzzard at Imperial, as a good friend and colleague of mine, he points out the absolute necessity of MathLib. The reason for that, he gives this wonderful talk where he puts 2 papers in the Annals of Mathematics. So this is arguably the most peer-reviewed journal in all of science. The review process is like 2 to 3 years. So it has 25 published papers since the time of Hilbert, and the review is brutal, right? And you just keep them. Andrew Wiles' proof of Fermat's last theorem, for example, is in this Annals of Mathematics. He shows 2 abstracts of Annals of Mathematics where the abstracts are mutually contradictory. So at least one of them is wrong. It has escaped the most severe peer review process known to man. So he says, we've reached the point in mathematics, it is absolutely crucial to use MathLib to check every single step of the proofs. And whatever it takes to start typing every one of these bits in. So that's bottom up. Next part is top down. Now, what is top down mathematics? Well, back in the 20th century, the big turn of the 20th century, there were 2 schools of philosophy of mathematics, which vaguely went under formalism of David Hilbert and intuitionism of Levsin Brouwer, 2 great giants of the time. Of course, Hilbert is certainly one of the greatest mathematicians of all time. Hilbert was trying to push for formalism, this idea that mathematics should be built from ground up. Every single sentence must be logically followed from every other one. In fact, Hilbert's push in this agenda was part of the inspiration for Principia Mathematica. On the other hand, Brouwer was trying to push for this idea that mathematics is a creation of the human mind. That you don't have to have absolute positives and negatives, right? That, by the way, this is you've just exhausted the entirety of my knowledge of mathematical philosophy, and that's it. So I'm not a philosopher, so that's it. So if you think about what bottom up is the guy with the cool hat, top down is somewhat in this idea, right? So let me make that a little more precise. It's very somber. It suddenly got very somber because of this slide. Oh, by the way, the slides, I'm extremely grateful to Roman Rybyansky, who is our designer at the London Institute, who has done this fantastic job at making this slide. I give him some slides which look like crap, then he... Now, it brightens up. So this goes under the rubric, this intuition-based mathematics goes under the name of experimental mathematics. Now, you may not think mathematics is experimental science, but it is. It's just a different type of experiment. I mean, you think about experiments in terms of like CERN, Kobe surveys or whatever. But mathematics is a heavily experimental science in the following sense. We muck around and try to do, here's another sequence, this integral, maybe it works, it doesn't scratch, paper waste basket, blah, blah, blah. That's kind of get kind of data-oriented mathematics, right? And this is why we love blackboards, because you can erase it immediately, right? Upstairs at the London Institute, we have beautiful blackboards. And in fact, there's a wonderful piece by Theo Zenu called The Magic of the Blackboard. And we like it precisely because we can experiment, erase, experiment with all kinds of ideas, right? So this is a field where we muck about, and it's great fun. It's the only thing more fun than doing mathematics is to do it with a colleague on a blackboard, because it's kind of, all right. So I quote the great Vladimir Arnold, a Soviet mathematician, certainly one of the greatest mathematicians of the 20th century. He said, half-jokingly, that mathematics is actually a branch of physics where the experiments are cheap. Now, it is cheap, right? Because, we don't build a machine to do this stuff. We can even use this stuff. We can calculate. I have some Magma software installed on my phone, so I can play around with number theory game experiments. And in fact, by the way, we have in the London Institute, we've established the Arnold program. We have several Arnold fellows present here today who celebrate the life and the works of Arnold. This is one of the sanctuary fellowships that we've established since the Russian-Ukrainian war. So we're very, very lucky to have these scientists with us. So to give you an example, I'm going to give you two examples of experimental mathematics. The first example comes from the greatest neural network of the 19th century. Clearly, the greatest neural network of the 19th century, if not of all time, is the brain of Carl Friedrich Gauss, the prince of mathematics. Here's a neural network that was not artificial. It was created from the divine powers, and it just happened to reside somewhere here in this little black bit. That neural network was able to do the following experiment. When he was 16, Gauss was bored. So instead of playing football, he plotted the number of prime numbers less than a given real positive number. Okay, prime numbers we've known since the time of Euclid, 2, 3, 5, things that cannot divide by anything except 1 and the number itself. But Gauss did this strange thing of just trying to count up to a certain number. So for example, if I give you 7.8, how many primes are less than 7.8? Well, 2, 3, 5, 7, they're 4. So that number is 4, and so on and so forth. So this made a continuous plot, okay? Well, Gauss looked at this when he was 16 and not playing football and said, this is clearly x over log x. Like, seriously? Okay, let me just give you an idea of the limitation. Gauss had to compute by hand. They had tables of prime numbers up to the 100,000 range, and he had to compute further by hand. It took him weeks, the ones higher than that. Got a few of them wrong, in fact, but it doesn't matter in the grand scheme. And did this plot, it's number one. So you can imagine, with today's technology, right, how much faster we can do this kind of experiments. Right, that's first thing. Two, statistics didn't exist then. So Gauss had to invent statistics and regression. In fact, the idea of regression was invented by Gauss to solve this problem, all by the young age of 16. It probably took him just about a couple of months, that's it. And then he said, this is clearly x over logs. The regression is this idea of the best fit, right? Which we take for granted, but at the time, there's no technology. He had to invent statistics to have this best fit. X over log x. Anyhow, and that was known as a conjecture, right? You play with mathematical data of this type, right? And then you come up with an idea, conjecture. It looks like this, but how do you prove it? Now, interestingly, the proof of this fact, which is now known as the prime number theorem, had to wait 50 years for de la Valle-Poussin and Hadamard to prove this, that this is indeed approximately x over log x. Because you had to wait for Cauchy and Riemann to invent complex analysis to give you the technique to prove it. So that's a great example of experimental mathematics. How did Gauss know? This is why he's called the Prince of Mathematics. Right? So that's the first example. Now, here's a bit interesting bit. Now, you all know what the Millennium Prize problems are, right? They're the 7 problems decided by the Clay Foundation in coordination with all of the greatest mathematicians on the planet. At the turn of the century, in 2000, they decided what the 7 open problems in mathematics are that are most relevant. Okay. In about 10 years, one of them was cracked. Each one of them had a $1 million price tag. You solve them. It's probably the hardest way to get $1 million. You're better off trying to rob a bank and get away with it than to actually solve one of these problems. Grisha Perelman solved one of the 7 and declined the $1 million because he said he did it out of love. I mean, this is as beautiful a mathematician as he ever gets. And now he's living like a penniless guy. He's a poor guy. He's like hanging out on the streets of St. Petersburg. Anyhow, there are 6 of them left. And what's really not emphasized is that of the remaining 6, 2 of them came from experimentation. The most famous problem of mathematics, of all of mathematics, is probably the Riemann hypothesis, posited by Riemann in 1859. I won't get you into the details of this. I can give an entire lecture just on the Riemann hypothesis. This is like the most beautiful problem ever. Right? And then in 1959, in a footnote to one of his papers, he speculated by checking the first 20 or so of zeros of what's now known as the Riemann zeta function. And they kind of lie on this line that's orange. And he says, I think it's true for all of them. That's it. Mathematicians are very good at writing footnotes. Our footnotes are, that's where all the gold is, right? Like things like 1 + 1 might be useful someday. This line, and then the speculation, by checking 20 or so, because that's what technology allowed him at the time, to be all among this, is the single most important problem in all of mathematics. You prove this, you don't just get $1 million, you will be the greatest mathematician that ever lived. Anyhow, but this came from experimentation. It was just Riemann mucking about, trying to calculate the critical zeros for Riemann zeta function. That's it. The other one is even more interesting. The conjecture of Birch and Swinnerton-Dyer. So Brian Birch and Peter Swinnerton-Dyer, back in the 1960s, were able to use this ETSAC computer in the basement of Cambridge University. So you can see what I'm getting, right? So mathematicians are good at footnotes and basements. So this giant object they were able to use, I don't even know what this does. I mean, I don't even know where the button is to push. This is really remarkable stuff, right? And yet it occurred to them to use this machine to plot what's known as ranks and conductors of these things called elliptic curves. I'm going to come back to this conjecture of BST, this open problem. And they noted a pattern, and they made a conjecture. And that is actually one of the first major conjectures ever raised by computer assistants. And it's still open, right? This one has been open since 1859. This has been open since the 1960s. And if you please work on it, just, in fact, drop everything else, just work on this. This is much, much more rewarding than anything else you're doing in life. So that's, right? So backtrack a bit. Gauss, using the eyeballs, and his phenomenal neural network was able to come up with prime number theorem, which was proved 50 years later, or conjecture then became prime number theorem. These 2 of the 6 Millennium Prize problems came about from experimental mathematics. Since this is the age of AI and internet, I got this this is not me, this is too clever to be me. Some dude put this meme on the internet, and I think it's really very appropriate to describe experimental mathematics, in some sense that we've always done this, we just don't admit it. Right? So, that's what top-down mathematics. It's like humans flying over this landscape of math and trying to see patterns and try to come up and formulate problems. Can AI, and how can AI help us in this direction? Right? So how can AI help find a problem to work on? Not just trying to find the proof of something that you know to be true and then type out every single foundational sentence, but how to actually have this intuition of finding the right problem to work on. So in mathematics, this is called conjecture formulation. My friend Challenger Mishra here, I think, he works on this field of formulating conjectures, and it's very much something that we work on together. So, since 2017, when my son got me into this whole thing, it's now a very vibrant community of mathematicians, of hundreds of us together, and hundreds of papers are written. I probably contributed 50 of those papers. It's a vibrant community in trying to use AI to try to come up with new ideas and new mathematics. Okay? There was this one beautiful paper, DeepMind collaboration, with a whole bunch of authors, Alex Davis from DeepMind, and Jody Williamson and friends, where they actually discovered a new formula for in this field of knot invariance by letting AI look at data known as Jones polynomials. So we're already at this stage. And I had the fortune of having many, many friends and collaborators and students. And I think my talented students, Ed Hurst and Ellie Hayes, are here, that wrote many enjoyable papers with them, in just trying to discover new problems for mathematicians to actually work on. So this is a very, very vibrant field. So because there's been all of this stuff about AI-assisted discovery in mathematics, we thought it's probably a good idea to come up with a stringent test. What would be a good AI-assisted mathematical discovery? Right? Now, in 2023, I organized a conference with a bunch of friends at the Isaac Newton Institute in Cambridge, just to bring different people together. Kevin Buzzard was there, and various people that joined online and from distance. And there we tried to formulate a test that would be tough for AI, right? Because ChatGPT actually has passed the Turing test in 2022, I'm going to get back to that, we needed something that's another level for AI-assisted mathematical discovery. Right? And that, we named it the Birch test, partially inspired by watching a video. Birch couldn't join us. He's 96, by the way, so he's kind of excused. But by watching a video that he presented, and we jokingly, with Kevin Buzzard and friends, we named this the Birch test. And I reported this with my colleague Misha Burtsev, whose wonderful talk on large language models on DNA was given here a few weeks ago. We wrote this as a correspondence for Nature, just to propose this Birch test. So what is the Birch test? It's AIN for AI. The A stands for automatic. It has to be an automatic thing. You can't have, like, I feed you some mathematical data, then I'm going, oh, humans, oh, no, this bit is useful, this bit is not. Feed it in and do nothing and let it run. Second of all, it has to be interpretable. Now, this second one kills my early papers in 2017, because I gave you a neural network that was able to predict topological invariance given geometries and manifolds. But that neural network is useless to a mathematician. It's just like, this is a computer program. What are you going to do with it? Like, there's no equation I can try to prove. Third of all, it has to be non-trivial, in the sense that it has to raise a conjecture that people will get interested to work on. I'm sure if you feed enough data into a machine now, AI, ChatGPT, whatever, they're going to say things like 5 plus 7 is greater than 2. Yeah, it's certainly true, and you can prove it, but that's too trivial. It's not interesting enough, right? So here, I'm going to let you form your own opinion. So far, in the last 8 years, nothing has passed the Birch test. We got very, very, very close a couple of times. And I'm going to explain just what I mean by the couple of times. And, oh, by the way, I learned from our science writer, Tom Hodgkinson. By the way, I'm very grateful to Tom Hodgkinson and to Anano Bhattacharya, London Institute's science writers, who gave so much feedback. But from Tom, I learned the word, apparently to birch is a verb, Brian Birch is a famous mathematician, and this is a terrible thing, but I have to say it's because it's a funny joke. So apparently, back in the day when schoolboys got caned, you use a birch branch to do it. I'm glad such barbaric things are not done anymore. I certainly don't do this to my children, but I tell them about it. And I say, I say, look, if you don't practice your violin, I will birch you. So here's the Birch test, named after Brian Birch. So what is interesting is that this test, I mean, it just so happens that Brian Birch of the Birch-Swinnerton-Dyer conjecture, his name is a verb we're using to birch an AI system. That's fine. You can beat the machine as much as you want. And you can take this Birch and just try to beat it. Can it raise a conjecture or a problem interesting enough for human mathematicians to work on, right? So we got close to passing the Birch test twice out of the hundreds of papers so far. So the first instance was that famous DeepMind paper that I mentioned. That, unfortunately, didn't pass the end test. They were able to prove the conjecture themselves within a month. I like this one, no bias at all. But there was the other time that we got this close to the Birch test, and this is with joint work with Lee, Oliver, and Postnikov. I think Oliver might be in the audience. Thanks, Tom. With this, I'm not going to bore you with this, but what we did here was to take elliptic curves, some of my favorite things, in the spirit of Birch and Swinnerton-Dyer, take the data. The data has been compiled in this database called LMFDB. It's a terrible name because it does, you have no idea what it stands for. I'll tell you what it stands for later. But this thing, it's got 3.5 million elliptic curves, and then we took this data, we fed it into neural networks, and it was able to predict certain things that's related to the BSD conjecture. That doesn't pass the eye test, right? That's not interpretable. But we were able to inch out a precise conjecture, a formula, and then we wrote an email to Peter Sarnak and Andrew Sutherland, who are the leading number theorists of our time, and said, have you seen this formula before? And we thought that Peter Sarnak is going to write back, and he says, yeah, I did that when I was 5. But he wrote back and he says, my goodness, I have never seen anything like it. In fact, Birch could have made this conjecture, but he didn't. What did you guys do to raise this conjecture? And we told him we actually used data, AI techniques, principal component analysis, support vector machines, and neural networks, and then we inched out a precise conjecture. This conjecture is still open. It's been 3 years. The entire community of number theory in this area of L functions and elliptic curves are still working on it as I speak. It was the first conjecture to be raised by an AI human interface that defied all of the top minds in the field. Now, it doesn't pass the Birch test because when we raised this conjecture, it was an interaction between humans and machine. Right? So that broke the A test. When you can just feed the data, then you can start giving stuff on its own. That's a whole brave new world. This was I'm proud to say that this was covered by Quantum magazine to be one of the major breakthroughs of 2024, because this was the time when an AI system raised a conjecture that defied humans. Catch me outside and I'll explain for you for hours what the murmuration conjectures are. It's called murmuration because it kind of reminded you of the murmurations of starlings. It has nothing to do with murmurations of starlings. These things when birds do their thing. This is murmurations of elliptic curves. So, final bit is metamathematics. I said there are 3 ways in which we do mathematics and 3 ways in which AI will help us to do mathematics. The final one, and this one is perhaps the most mysterious of them all. Okay, for lack of words, I called it meta just because meta sounded cool, but because you're kind of outside of mathematics, like physics, metaphysics, mathematics, metamathematics. So what is this? Well, it's the world of large language models, ChatGPT, DeepSeek, whatever. Can these things do math? Right? ChatGPT gives you all kinds of nonsense, right? And mathematics is a very, very, very stringent and rigorous subject. Can these things ever produce anything of interest to mathematicians? Surprisingly, the answer is yes. Okay, so we're very positive on this direction. So as I said, remembering I put the Turing test of 1949 to be one of the highlights in human history. Actually, I'm surprised that this is not reported on every single news outlet. In 2022, ChatGPT has passed the Turing test. We now can no longer tell whether you're interacting with a human or a machine. That's how powerful large language models are. These are large language models, again, are based on neural networks that kind of statistically inference how you can predict the words, right? Think of ChatGPT as Google+++. You know, when you type in Google, it kind of auto-completes. ChatGPT, all these language models is essentially this completion. It kind of predicts what's likely to be the next thing, right? So it's passed the Turing test, and where are we on that? Well, so there is this thing called the International Math Olympiad. This is probably the most difficult high school level mathematics you can ever imagine. Think about all the poor Chinese kids, Russian kids, Korean kids who are being birched since the age of 4 to just pass this exam. This is one of the most competitive exams in history ever devised. Really, really, really hard problems. And this thing called the IMO Grand Challenge is, can you use some kind of AI, broadly defined, to try to pass one of these tests? Okay? 2024, combinations of alpha geometry 2 by DeepMind and alpha proof, which actually includes MathLib, bits of MathLib, was able to get a silver medal. People were like, oh, wow. Well, think about that, right? So these are really hard high score problems. You can add this kind of geometry. If I stare at it, I won't be able to do it. I mean, give me a couple of weeks, maybe I can do one of them. And 2025, just a couple of months ago, Gemini DeepThink got the gold medal for this. I mean, this is in the sense that I'm going to give you one of these questions that's really, really, really challenging, and these language models can look at it and give you full solution, and then be graded by humans, the IMO president here, and graded, and then to give you a mark. And it's already beating the best humans, kind of like AlphaGo beating humans in 2012. We have reached this stage. Now, I know exactly what you're thinking. You're thinking, but this is just really, really, really hard high school level problem, right? What about actual research mathematics? Okay. Well, there is that. So OpenAI funded this company called Epoch AI, which does benchmarking for AI. And they launched this program called the Frontier Math Project. So Frontier Math is exactly the research level analog of things like DeepThink passing the IMO test, the gold medal on the International Math Olympiad. So they did several tiers. I was involved in the last evaluation one, which is called Tier 4 problem. So what they did, they flew 30 of us into their headquarters in Berkeley, and we signed an NDA, and they locked us up in a room, human mathematicians. 30 of my colleagues from all around the world, they locked us in, and we were fed very well. And all we did was to try to come up with a set of 40 problems that I would give to a colleague or to a very advanced PhD student or postdoc, and try to see whether one of these language models or the GPT plus models could actually solve. GPT-5, at the time it's 441 mini. To be fair, these questions are phrased in the following way. You must have a precise numerical answer that's like 10, 20 digits long. So there's no way for it to guess. Okay, I'm going to show you an example in a minute. And of course, GPT can give you proofs, right? But it's too hard for humans to evaluate. With math questions that have a precise numerical value, you can just look at it, it's either wrong or not, and then has it reasoned in the direction towards that. So we did this, and then word got around, and it was reported by various news outlets. And I have achieved the dream of my life, which is to appear in the sun, and fully clothed. And this became a secret meeting for mathematicians just trying to beat AI. And this was known as the Tier 4 problem. So very briefly, tier 1 to 3 are some of the preliminary ones. There are 300 of those. But the tier 4 results, we're getting something on the order of 10%. So the benchmark just finished last month. And so May, they took a few months for OpenAI, for GPT, some version of DeepThink or GPT. And they benchmark how all of these language models performed on these mathematical problems. Okay, I want to emphasize again, language models, are they reasoning? I have no idea. I mean, that's for philosophers to decide. But all I know is that this benchmark shows that 10% of the time, you can actually get a precise answer with the right amount of reasoning. To give you an idea of how hard a tier 4 problem is, here's an example. I can't remember whether this one was one of the 10% that was actually solved now, but just read it. I mean, unless you are an analytic number theorist working in the field of L functions and elliptic curves, even in that specialized field, even a mathematician not in that field would not even understand this question. Right? And this level of problems, at 10% of the time, can now be solved by large language models. Why? Because large language models has the entirety of the internet of every single paper that's ever written, and it's just doing pattern matching in that direction. And it's now pattern matching so well it can solve problems like this. I have a colleague during that meeting of the secret meeting of 30 who said to me, "I'm sacrificing one of my papers to be here because I'm coming up with a problem to give to you. I'm signing an NDA on something I should actually be publishing in the journal, right? But because I signed this, I'm going to just feed this into some version of a language model, and so that I won't. So that's how hard these problems are. These are actual research problems. So we have reached this point as of this year. It's remarkable, 2025, right? We've got gold, IMO. We have Frontier 4. You see where Frontier 5 is going. Tier 5 of Frontier Math, which should be launched next year, which is open problems. Can it solve problems that humans cannot solve yet? We're getting there. I mean, we live in arguably the most exciting era of mathematics in human history, since the time of Euclid. So, to conclude, has AI so far solved any major open conjectures in mathematics? No. We're getting there. Is AI beginning to help to advance mathematical discovery? Sure. Since 2017, there have been all the hundreds of papers that have shown that this is possible. Has it changed my day-to-day routine as a mathematician? Yes and no. I've certainly changed the habit of coding in experimental mathematics because I asked GPT to write most of my code now. And in fact, I asked GPT to find citations. Why can I trust it to do that? Because I can then look at the paper myself if it's the right citation. I'm certainly not going to trust it to do a proof for me, to probably go on, but I'm interacting with it. There was just a paper out last week or 2 weeks ago where a bunch of mathematicians in combinatorics interacted with GPT and they inched out a new idea which helped them to actually prove a theorem. So we're really, really getting there. So now you would think that since we're in this new age of mathematics, every funding agency is jumping to this, right? I began by quoting the thing that started the word artificial intelligence. That started with a grant proposal. Here are some of the referee reports that I got from my recent grant proposal submitted to the UKRI. You can see that mathematicians are rather conservative in their judgment. And subsequently, the funding agencies in this country are conservative because of such reviews. Now, there are centers in China. There's a center for AI for mathematics called BIMSA in Beijing. There is a center in Boston, MIT, and Northeastern called IFI. There's the Center for AI for Mathematics in Max Planck in Germany. Somehow the UK doesn't have one yet. So visionaries out there, online or here, please fund this exciting direction. So it's clear, I hope I have given you an idea of what the future of mathematics is, and that clearly is the human working in tandem with AI, and we're not computing. I don't think we're competing in any way. This is not, they're trying to take over jobs and kill us. In trying to solve the most fundamental problems in mathematical discovery from bottom up, top down, and metamathematics. So thank you very much for your attention.